Hi, welcome back to another episode of Real-World Serverless, a podcast where I speak with real-world practitioners and get their stories from the trenches. Today, I'm joined by Richard Davison, who's a senior solution architect at AWS and who's been working on the exciting LLRT or low latency runtime for Lambda. Hey, man, welcome to the show.
Thank you, Jan. I really appreciate it. Thanks for having me.
Yeah, so I guess before we get into it, do you want to spend about a few moments just to talk about your experience and what you've been working on at AWS before we dive into LLRT?
Sure. So I'm Richard. I work as a solution architect in the partner organizations. I work mainly with partners to help them drive the adoption of modern applications, as we call it. So that means serverless and container applications. So I've been with AWS for 3 years now. And I've been working with this project, not full time, but as kind of as a pet project for almost or close to 2 years now. So I'm really happy to see that I finally pushed the button to make it open source.
Wow, this okay. So I didn't realize it's been such a long time. But yeah, for those of you who hasn't seen it, the announcement, I think the official announcement was about a month ago. I want to say it was publicly
just
announced.
3 weeks, something like that. Yeah.
Yeah. So maybe I can share my screen because in case anyone haven't seen it yet, let me share my screen. So the LLRT project, or the low latency runtime for Lambda, is a specialized runtime for JavaScript, which promises some pretty significant improvements in terms of the startup time, which is something that a lot of people still talk about when they're considering Lambda as a general purpose compute platform in terms of the cold start time. And the improvements here are pretty important. But when I did some tests for myself, I actually found that it was actually even more impressive than the numbers suggest. I had a Lambda function, which is just I think calls DynamoDB. I think that's all it does. The cold start went from about 750 milliseconds to I think just under 50 milliseconds. Hold on, let me just quickly bring that up. I was really impressed by the numbers that I was seeing. So I wanted to bring Richard on the show and just talk about there they go. Yeah, the number I was seeing with my Node 18 function was almost 750, but then with just making the changes to run on LLRT, it was brought down to 50, and on a few runs it was under 50 milliseconds as well, which is really, really impressive. And so I've got a whole bunch of questions about how you managed to do that. And one of the big headlines we saw was, it's using Rust. So there's a lot of assumptions about why that's fast. But I guess maybe before we get into that, can we start from the top and just maybe tell us what is the motivation behind building this custom runtime for Lambda?
Yeah, so I'm happy to talk about that because there's a lot of nuance to this. And as you know, as a fellow serverless evangelist and a serverless enthusiast, there is quite a few discussions going on about the drawbacks of serverless. And one of those discussions have mainly evolved around the introduction of cold start. So when, for the first time, when the Lambda service loads your function code, it takes a little longer time than it does once we have that loaded into the system. And this can introduce some latency, and that's often referred to as a cold start. And it can be one of those things that it become a bit frustrating for workloads that have a very strict resource requirements, or latency requirements rather, which makes some workloads not applicable or less desirable. And in this world of modern applications that we live in today, users expect swift responses, where kind of every action triggers an immediate response. You don't want to have that cold starts. In reality, cold start is not really a huge problem because they represent typically between less than 1% and around a few percent of all invocations. So in production workloads with a lot of invocations, cold start is not like a major problem, but still it can be disruptive to that seamless user experience that the customers and users are expecting. So I've done a lot of work, like both internally and externally, before I joined AWS to try to mitigate these cold starts and see what we can do about it. We have a lot of initiatives going on at AWS to try to work around the limitations, but that has currently been one of the drawbacks by having the serverless first approach, is that there has to be, what's the caveats, what's the things that you have to think about, and cold start has been one of them. At reInvent, not this reInvent, but last reInvent, we introduced something called Snap Start for Java workloads that allow you, it takes kind of a different approach that allows you to store a snapshot of your application's state and memory and everything and restore that, which can be faster, especially since Java applications takes a while to spin up. There is no such equivalent yet for other types of runtimes, such as Node or Python. We're working on it, but I wanted to take a different approach. So in the current state, we basically build runtimes for AWS Lambdas. We have a bunch of runtimes. We have Python, we have .NET, we have Java, we have Bring Your Own, and we have Node.js, and etc. So we have a lot of already provided runtimes. But these runtimes were not specifically built from the ground up to work in the resource constraints that Lambda has. So they are more general purpose. And we're now taking a general purpose programming model and execution, and we're putting it into an ephemeral environment, and we're putting it into a very resource constrained environment. So that might come with some trade-offs. It works really, really well. But my kind of take on this was, if I start from the ground up, can I make it better? Can I make something specifically tailored for this type of environment where startup matters, but also resources really matter? So make something that is very sparse on resources, that has really fast execution, that supports the dynamic language, and that is like purposely built for this environment rather than to take a general purpose and make it adopted. So start from the ground up. And I found out also, being having worked with Node for more than 10 years, and of course, the popularity of Node ecosystem and JavaScript ecosystem as a whole, it's a perfectly good candidate to start to work with. And another benefit of working with JavaScript is that it's mainly a specification, and it has a lot of different implementations in terms of different JavaScript engines. And the offerings that exist today mainly uses browser-based JavaScript engines that have diverged from web browsers such as Safari or Chrome. So your audience may of course know about the V8 engine or also the JavaScript core engine that comes from Safari, and the V8 engine comes from Chrome. So those types of engines are extremely capable. They have a very fast execution, but they require a bit of time in order to become that efficient, which is a characteristic not ideal for fast startup. So they were basically built for web browsers. So it doesn't really matter if your web browser starts in 200 milliseconds or 300 milliseconds, but it can have a huge impact when running, for instance, in a Lambda function. That being said, there have been numerous efforts to try to improve the startup performance of these JavaScript engines. My approach was to take a simpler engine that was written by Fabrice Bellard and Chalice Gordon. I probably butchered those pronunciations. Fantastically skilled programmers that are the minds behind FFmpeg and QEMU and many other projects that have written an engine called QuickJS. So QuickJS is an extremely lightweight but very capable JavaScript engine. So by incorporating a very, very lightweight engine that doesn't require a lot of resources, I can kind of mitigate the cold start problem and have an extremely fast startup. So taking a kind of a completely different approach, so starting from the resources that are constrained and working from there and try to make it as good of an experience as possible.
Yeah, I think that makes sense when when you're talking about a specialized execution environment like Lambda, rather than trying to see how can we fit existing ecosystems into it. I think it totally makes sense for you to ask a question, go back to the foundations and see
exactly
what would a good JavaScript runtime look like for this specific environment? And I think, like you said, a lot of people that are starting with Lambda today are probably overthinking about cold starts, because in practice, a lot of the web traffic would be quite, bell curve, and they're quite stable. But I have seen a few cases where you do have fairly unpredictable spike in traffic. That's where you tend to have to think about, okay, what's the impact of cold starts? And also when you have more complicated microservices environment where APIs call APIs, so cold starts can stack up. I mean, there are a few cases where cold starts is a really legitimate issue that people have to think about, especially if they're running with Java or .NET. So that's where you got things like snap start and provision concurrency. But JavaScript is still something that everyone uses. I keep watching and reading about people now switching to Rust because Rust is so much faster. That's great. And I think on the individual level, learning Rust or some other programming languages is great. And you can benefit from that in your work with Lambda, but it's not feasible to say, let's just rewrite every single application that's already out there and retrain all the teams. Thousands and tens of thousands of engineers already are familiar with JavaScript. We can't just go out and replace all of them or retrain all of them. So, having some way to improve the experience of the existing JavaScript applications, I think that is really, really key. And you touched on something that I was going to ask you about, which is how does this new runtime differ from alternative runtimes? Like you talked about VA, you talked about the one that comes with Mozilla, but there's also been Bun. That's been quite a big I guess a big hit recently as well. It made a lot of noise for being more compact, more lightweight, and faster as well. So I guess is your answer? If I was to ask you what differs LLRT from something like Bun, what would you say?
Yeah, so that's a really good question, and these are like fundamentally different approaches. So LLRT is not meant to compete with either Bun or Node, because it takes a very different approach that obviously has some drawbacks. But if you start at what's the fundamental difference? The fundamental difference is mainly the engine. And another fundamental difference is the approach that we take. So if we start with Node, it's an extremely capable project, and I'm very amazed by how far they've come with Node since I've started using it more than 10 years ago. It's very stable and it works across a large chunk of operating systems, even mobile devices, Raspberry Pis, everything and everywhere seems to be able to run Node, which is a part of their strategy. So their focus has been a lot on both growing the ecosystem and being a project that it's easy to contribute to, with a large of its code footprint being implemented actually in JavaScript. And it supports a wide range of operating systems and devices. I think that focus has shifted a bit now to try to introduce more performance and startup and things like that as well. But backwards compatibility is also something that is extremely important for the Node project, because there are millions upon millions of projects that depend on it. So it's very easy to come in with an approach that I have done and say that it's massively faster in some use cases because I don't have that legacy, and I don't have to support all those devices, and I don't have to support all those APIs, etc. So it would not be fair to say that this is so much faster because it's better. It's a very different approach, and it's not meant to compete with that project. And then we have Bun, which is also an engineering marvel and an achievement. I think Jared that has made Bun. I mean, I listened to a lot of podcasts when he's been speaking and presenting, and I've looked at what we have, and I used it also myself, and it's a very, very capable runtime. Also, a bit of a different use case. It's more general purpose, and it also distinguishes itself by being an all-in-one toolkit, which in contrast to Node, that you have to have external packages and binaries for doing like package management with npm, or installing dependencies, bundling, running TypeScript, etc. All of this is baked into one single toolkit, which makes it a fantastic developer experience. So where LLRT sits aside is that it's purposely built again for serverless environments. it can run on other environments than Lambda, but it's built for environments with low resources. So I don't want it to run TypeScript, and I don't want it to have too big of an API footprint, because that will add to the start time. So for instance, imagine that we add, or if we wanted to put TypeScript support in Lambda, we can pull in a Rust dependency that does the transpilation on the fly, and then we load that transpiled JavaScript or that transpiled TypeScript into the engine and execute it. But that will add significant cold start time, which is a trait that we really want to avoid. So we rather see that you keep your existing tooling. I mean, you can even use Bun to bundle and package JavaScript for LLRT, right? If you just use the transpilation. And so the focus has kind of been to keep the core extremely lightweight and do the computationally intensive things as much as possible at compile time. So that's why focus has been to keep a lighter API. However, right now it's very light. It's nowhere near as feature complete as we want it to be, nor is it nowhere near supporting as many APIs or have as large API footprint as neither Bun or Dino. But again, it's a bit of a different use case. Where we want to be eventually is to have what's called winter CG compliance. So winter CG is a working group that tries to where it's an incentive to have a shared common set of APIs across different runtimes. So across runtimes running on Cloudflare workers, Dino, Bun, I'm not sure if Node is in there or not, but to have a common set of APIs that allows users to pick and choose basically what satisfies their use cases. So in summary, LLRT sets itself aside by having a simpler, more lightweight approach, but in trade-off, you have also less APIs that are supported. But with that being said, we try to make the APIs that we actually support as close to the node specification as possible. This has a couple of benefits. This will allow you to, when you run into a corner, when you run into an API that you actually need, but it isn't supported, it isn't implemented, you can switch back to Node and your effort aren't wasted. And I think this is really important, because I don't want people to build specifically for LLRT, run into a corner, and then all of that job is wasted. It's a better approach. I reckon it's a better approach to have something that tries to adhere to a specification already defined that allow you to switch back once you hit that corner. Another very important distinction is that since the engine is even though it's very capable and supports ECMAScript 2020, it doesn't contain a just-in-time compiler. The just-in-time compiler is a fantastic and a very sophisticated piece of technological achievement that allows you to compile and optimize JavaScript code on the fly and translating it to machine code, which will make it very, very efficient. However, that compilation and that translation of JavaScript code into native machine code, it takes resources. It requires a lot of memory, and it requires a lot of CPU. That's why you may see in a very resource-constrained environment that has a short lifetime, you will see spikes. You can see some latencies going up for no obvious reason, even though your payload was almost the same or your event looked almost the same, but you have a latency spike. And this is mainly because it's just-in-time compiler. It has to evict compiled code and methods from its compile cache. So it's a very complicated piece of technology. It works really well for long-running tasks where it can find the best ways how to optimize your JavaScript functions while running for a long time. But it takes away some of that precious compute that we can use to execute the code because it needs that for compiling the code. So both Dino and Bun are using it, and it has, of course, significant performance benefits for longer running tasks or loops that iterate over hundreds of thousands of objects or call functions 10,000, 100,000, a million times, we won't see near the performance in LLRT, since it's purely what is called interpreted. So what you see on every line is basically what gets executed by the engine. So that's also fundamentally different.
Right, that's really interesting. On the performance side of things and the comparison with Bun, when the Bun came out and they made all of these performance claims, one of the things that got a lot of pushback from the Node team is that, you just basically threw away a lot of the backward compatibility that we care so much about. And so, the Node team has to carry, Node is 15 years old by now. So there's a lot of baggages that people's been building on top of that they haven't been able to remove. So they can't just take down the entire house and build from scratch. They have to worry about the people that are living in there already. And
exactly.
So Bun is able to make decisions that the Node team can't. So they can't make optimizations that the Bun team is able to, take a hammer to it. And I understand that you guys are doing something, like you said, that you're not using JIT compilation because it's a very different execution environment compared to a long-running process, a server that's going to be sitting there for weeks, months, maybe years at a time. You can just optimize for that. But in that case, are there any performance differences that are noticeable for the kind of workload that people often run? Because when I think about the stuff that I do in my Lambda functions, a lot of them are I/O heavy. Very, very, very rarely will I have a Lambda function that are doing something compute intensive. So I would think that the lack of JIT is not going to hurt my performance too much. But from your benchmarks, from testing, have you seen any sort of evidence in terms of, what sort of performance difference would you be seeing?
Yeah. So your assumption is exactly right. So where LLRT kind of focuses right now is to be like that kind of the glue code, right? When you do I/O intensive more than you do compute intensive. So for instance, if you do like a simulation or some heavy calculation, say that you do a lot of hash calculations inside of JavaScript, that would not be a good use case, because that's really where a JIT compiler shines, right? Where you can find that that compile path and that optimization based on profiling of the function calls to find, how can I make this into machine code and how can I execute this? So you see also all over across the internet, you see benchmarks doing like hello world web servers and things like that, which I think is benchmarks are really complicated. It's hard to prove something with a benchmark. I think it's easier to focus on real world use cases, putting something somewhere where you have downstream dependencies on I/O or on network or things like that, because that gives a more real world, even though it's still synthetic, right? But it gives somewhat closer to something actual than a hello world web server can do. So in terms of that, even interpreted performance could be improved. There are other runtimes that doesn't have a JIT compiler that performs better than LLRT. But what we've seen in tests, and our focus has also been right now to support AWS SDK version 3. So doing integrations with AWS SDK, fetching files from S3, putting things on DynamoDB, fetching data, doing that glue code, communicating between services, that has some significant performance improvements in comparison with others. And that's also not only for cold starts, but also for warm starts, mainly because that the lack of a JIT and a simpler engine doesn't have some benefits in this case. And I know I read this on a blog post from the V8 official blog. This was a couple of years ago, so that these numbers have probably changed. But they did some benchmarks running YouTube with Chrome and V8 engine without the just-in-time compiler and with the just-in-time compiler, and the difference was not huge. It of course was significant, but not enormous. I don't remember the numbers on top of my head, but it was something like 20% faster, which isn't an enormous difference in terms of the memory requirements and the CPU requirements it requires. So I mean, you can test this for yourself. So if you do like a very simple loop, or you put like a million items in an array and you run it with Node or LLRT or even Bun, right? You're going to see a massive performance regression with LLRT. But again, should you do that in a Lambda function, or are there better alternatives? And to your point, the best option would probably be for everyone to, or the fastest option would be for everyone to write their applications in a compiled language such as Rust or C++, but it's not as simple, right? People don't want to write it. They don't want to learn a new technology, and we have an existing ecosystem that of a lot of developers and a lot of tooling that already exists for different languages such as JavaScript and TypeScript that people want to use, basically. So it's not as simple as saying go write everything in Rust. I think that's it's a bit more nuanced than that.
Yeah. It's just, I mean, switching languages is very big, very disruptive change, and a lot of people just, well, like I said, they don't want to learn new things, or they don't see the value in the changing everything they're doing just to, I don't know, make your code a little bit faster when there's other options available, cheaper, less disruptive options available. And I guess in this case, so we've talked about some of the reasons why LLRT has got a really fast startup time. The fact that there's no JIT, the fact that there's a really lightweight, really lightweight engine without transpilation and all these other things. Are there also other, I guess, a trade-off that you have to make, at least conscious design decisions besides those two, to make sure that this runtime is very fast to start up? Are there any other major, I guess, contributing factors?
Yeah. So first of all, it's of course the limitations. Like, what are you doing in there? Are you doing compute intensive stuff like calculations of hundreds of thousands of times, or simulations or things like that? Measure and see, right? It can be good for performance. It can be horrible for performance. So that's like the first limitation. The second one is to look at the API coverage. We have that documented in our open source repository. So there's like an API.md in there that pretty much describes what it is. It can be improved. Not everything is covered that we support, but a lot of it is supported. So this is like what you're viewing here now on the screen is we have the high-level compatibility matrix, and we have a big sort of triangle warning signal there saying that even though I have a check mark for buffers, doesn't mean that the whole buffer class is supported. It's a subset, right? So everything that we support that has diverged from the node specification is partially supported. And you can go into the API.md file and look at in more detail where we have that compatibility matrix, more detail on actually what modules in there. So you see for buffer example, we have alloc, we have from, we have concat and byte length, and everything inherited from a typed array of uint8. Similarly with crypto, right? But again, we are working on bringing this to be Winter CG compliant, which adds a bunch of APIs, and we're constantly adding more. And it's also been really great to see that external contributors have increased and adding bug reports, which has been tremendously helpful. And also the early adopters. I really want to give like a shout out to the people that have been helping this project. And it has been so fantastic to see the reception so far. It has been overwhelming to see all the traction it gets. Even though this is not like an official AWS product, I think it's so fun to see that people are excited, people are willing to try it out, to test it, even in its early stage. And the bug reports that have been coming in has been like fantastic, really clear, really easy to follow up and find and patch. So that has been very helpful. So and it's such rewarding to see all the attention that this is getting. So I encourage people to try it out and find things, but be nice and remember that this is experimental. But hopefully we will have it a bit more capable soon. So we're working on it.
Right. So now that it's public facing, it's publicly available, people are able to try it out. Do you have a sense of what's the roadmap for this project for, say, the rest of 2024? If someone was to thinking about eventually using LLRT in production, what kind of expectations should they have?
Yeah, so right now it's an experimental package. So we don't recommend, to you should use it with caution, right? It can change at any time. I think we're pretty clear about that this is not an official AWS product. It's an AWS Labs. It's an experimental. This is us trying to figure out how we can make JavaScript an awesome place for, or Lambda an awesome place for JavaScript rather. But during 2024, we will work on Winter CG compliance. So once we have that in place, and it's still a bit of an evolving standard, there are some things in there that will be a bit tricky to implement. For instance, the Winter CG specification includes WebAssembly, which is, I think, to be honest, is something that will be a bit tricky to support in both in this engine and otherwise, because you basically have to bring in a WASM engine into it. So what people can expect during 2024 is more APIs added to support the Winter CG specification.
Yeah, that's good to hear. One of the things that I ran into as I was testing this out myself was that it didn't work with the Lambda Power Tools logger because they bring their own console object. And I think that's something that the LLR team runtime doesn't support just yet. There's a few things like that which hopefully will get ironed out so that for very basic use cases, things like I'm just writing a function that talks to S3 or DynamoDB, but I want my sort of tool set with me, my Lambda Power Tools, all of those capabilities that comes with logging and the metrics. I'd like to have all of those still available to me. So, I mean, once a few of these things are implemented, then I think that'll become a lot more usable.
Definitely. And we're working with the Power Tools team as well to see what we can bring in there. The biggest, I think, blocker right now is that even though we have streams added in, they're like polyfilled, so they're running in JavaScript, and they're not enabled for the AWS SDK v3. So there are some differences there. In order to get performance with this runtime, streams should be native, meaning that they should be implemented in Rust and not in JavaScript for this project, right? The Streams API is rather big and has a bunch of edge cases, so it also is part of the Winter CG compliance and the Winter CG specification. So that is something that we will prioritize to implement, so that it can work with piping and file streams, and also allow you not to be limited on memory. Right now, imagine if you want to download a big file from S3. All of that will now be downloaded into memory, so you work with it with a byte array. Not good, right? If you want to have 128 megabytes of allocated memory, the runtime takes some, and then you download a file and you run out of memory, right? So that's something that we really want to avoid. So having a streams support also in the SDK is something that we prioritize for coming weeks or months.
Yeah, that's a good point about the memory size, because with Lambda, you charge by the milliseconds, by the amount of memory allocated. So having a lighter weight runtime that require less memory can also have a cost benefit as well, not just in terms of performance and the latency. You mentioned the Rust there, and obviously a lot of people would read the headline that, this is built in Rust, and that's why it's fast. And we talk about some of the actual design trade-offs you've made, but how much of how much of that, how much does the Rust come into it? Obviously, there's the QuickJS engine that's written in Rust.
It's in C, actually. Yeah,
in C,
the engine is in C, but we're using a binding layer also from a third party, which is available on crates.io, so anyone can use it as well. It's a fantastic project that it makes it very easy to embed QuickJS engine. So QuickJS engine is in C, but all the APIs that we have implemented here are in Rust, exposing that. And of course, that's one of the major contributing factors to the performance, that has also been a design decision that we try to stay as much in native land as possible, meaning Rust and C, and as few and as little as possible in JavaScript, because again, it has to be evaluated on the fly. Whereas with a native approach, we can do it at compile time, so make very optimized things. For instance, JSON uses SIMD JSON, so single instruction, multiple data. So it can actually parse JSON extremely efficient thanks to the awesome SIMD JSON library and the bindings for Rust that exist. And that has also been a very it has been very good to work with Rust because of the ecosystem that has become really mature, and there are so many crates. That is like how we refer to Rust dependencies as crates that have everything in that you can think about in super optimized versions. So base64 encoding with SIMD, meaning that it's super fast. We do JSON escape using SIMD as well to do it more efficiently for bigger JSON strings and things like that all over the place. So we try to make it very efficient where we can and stick to Rust. So it has a huge impact on performance. And this is also similar to the approach that Bun does in comparison with Node. So as I mentioned before, a lot of the Node APIs are implemented in JavaScript. In contrast to where in LLRT, almost everything is implemented in Rust. In Bun, they also have a similar approach where everything is implemented in SIG, which is also a systems level programming language, right? So there are obviously some performance gains out of that, but the trade-off is that you sacrifice some maintainability and portability, right? So because Node has everything almost in JavaScript, it means that a lot of contributors can come in and fix issues and find bugs and contribute, whereas with SIG and Rust, that contributor capabilities are a bit more restricted because it's a bit more complicated to work with, especially if you don't have any previous experience. So if you come from like a JavaScript background, working with a JavaScript engine, it will be, I would argue that it will be even though it's of course very requires a lot of effort, it would be simpler to understand how the code behaves inside of Node than it would be to do in a completely foreign language such as Rust or C.
Yeah,
So it's a different approach.
And that kind of goes back to the point we were talking about earlier, that there's just far fewer Rust developers available, and that also makes it difficult for you to make that switch between, okay, let's rewrite everything in Rust because you just can't hire enough developers. So in this case, if someone wants to contribute towards the projects, what's the best thing for them to do right now?
Yeah, so the best way would be to check out the project and take a look in there, dive into the source code. It's not an overly complex source code. Again, a lot of the credit goes to the binding layer, or QuickJS as it's called, that has hidden a lot of the complexities, making it very simple to work with the QuickJS engine. So I don't want to take all the credit. So without both QuickJS and the binding layer, this would not have been possible, especially in this time frame. So I recommend to check out in there and try it out and find issues, find bugs that doesn't work, report it. There's also I have this on my backlog to add a list of basically all the WinterCG APIs that we don't support or that we partially support, and add it as issues, so people can come in and pick an issue and start working on features if they're interested in that. Some are simpler, others are more complicated that require substantial refactoring, such as streams, for instance. But I encourage you to take a look at, regardless if you're a Rust developer or if you're a JavaScript developer, just take a look at the source code. It's not super complicated. I have not worked with Rust for that long, for maybe I think it's close to 2 years now. And I also come from like a JavaScript Java background as well. So I think, just take a look in there and see and try it out and try to make it break so we can make it better and faster, right? And I got also a lot of questions from both internally and externally, like why don't you just make Node faster, right? Why don't you make it better for serverless? And I think it's a bit, again, going back to our previous conversation here, it's a very hard thing to do, especially, I mean, you can kind of argue that, if this was straightforward, someone would already have done it right now, because there are a lot of really smart people working on Node. And again, it's an extremely capable engine. And this is not trying to compete with it in any way. It's meant rather to complement and have other use case where it can achieve. It can work really well with constrained resources, right? And I think the biggest blocker for having a very, very low startup node is mainly that all of the APIs are in JavaScript. So it has to be JIT compiled, it has to be lexed and parsed and executed at runtime. But once you have that and it's up and running, it performs really, really well, right? So that's kind of the tricky part with Node right now. So yeah, again, I would also love to see an even faster Node, and I think we will get Node significantly faster at startup, especially with all the innovation that is happening right now, and it's an extremely capable project and very smart people working on it. So I'm sure it will just do improvements coming soon.
Yeah, but then their priorities were always going to be slightly different from yours, because the normal execution environment for Node is not the same as the Lambda function.
Exactly.
And so it's, you're never going to have that much influence in terms of pushing them towards prioritizing the thing that works best for you, but maybe not for most of their user base.
Exactly. Yeah, it's general purpose, right? It's by design. So it works on a lot of operating systems, on a lot of execution environments. It works really well on Lambda. It works everywhere, right? And it's like you said, it's a different use case. It's not like it's hard to compare. It's not an apples to apples comparison, because they have different use cases. The only thing that basically share right now is that some APIs kind of look the same, and they both run JavaScript. That's pretty much the commonalities in that.
Yeah, and the thing about the performance optimization is that a lot of times people gravitate towards one or two big headline items, like, oh, he's using Rust or using this engine or that engine. But when it boils down to it, most of it is just what do you drop? If you got to do X number of things, doesn't matter how efficient you can do it. There's only so much marginal gains you can make from those optimizations. And the biggest wins you're going to get is just by not doing certain things because they don't apply to you. And in your case, dropping JIT, dropping a lot of the transcompilation and things like that. That's the things that's going to make the biggest wins in terms of making it run fast in the Lambda execution environment. Because, like you said, the requirement is not the same as a long-running process.
Exactly. So, to your point, it wouldn't matter if you run, say you use Dino or Bun to run TypeScript directly, which is fantastic because you don't have an additional step. But then if you run it on a container workload, or if you run it on a traditional server, it doesn't really matter, right? Because it adds maybe a couple of milliseconds. Of course, depending on the size of your code base, but it adds some time that you don't care about because it's not important. But in a serverless manner, everything, every millisecond counts. So doing that ahead of time at compile time, which you do for other runtimes for Node that you already have those tools in place, that will give you the best possible performance. And it makes sense here also because this effort has been to have best performance. So if you can offload that and move step sooner in your deployment pipeline rather than having it at runtime, it will benefit. So it makes a lot of sense if you think about it.
Yeah, talking about TypeScript, another thing that I've always wanted for a long time is to have a native TypeScript runtime for Lambda. Because right now, the transpiling to JavaScript and bundling source maps is a tough decision. Either you have nonsense that stack trace, or you have this big source map that affects the cold start performance and affects surprisingly, the latency the first time you hit an error, I didn't realize how bad it was until you had this API that every now and then you see a big spike in latency. You'll be, okay, 100 milliseconds and then 3 seconds, and when I drive into it, and it turns out it was when you had an error the first time, because that's when the runtime has to load that whole source map to spit out a sensible stack trace. So that just makes it really uncomfortable, I guess, a trade-off that you have to make, a sacrifice you have to make.
Yeah, and again, falling back to previous conversation, I also had this conversation with a lot of customers saying, Lambda should have a TypeScript runtime, but I don't think that's actually what you want, because even though that it will improve the user experience or the developer experience, I would say significantly, and maybe address some of the concerns that you have, it will add to latency. So even though you don't have to ship a source map, it would still have to live somewhere. So that source map will now live in memory, where you don't have that disk latency, but it would still have to be reside somewhere, right? So it doesn't disappear just because we run TypeScript. It's just that it will be transpiled by the runtime at runtime. So you're now paying a latency. You will now have latency regression and have longer latency in favor of a better developer experience. So it's a matter of priority. So my argument here is like, if you shift that and do it as early as possible in the development lifecycle, do it at compile time, and you ship the source map in order to make sense of the stack trace, you will only have that spiky latency when an actual error occurs, right? And then you might have more severe problems than latency. So it depends a bit on how you want to see it. And of course, those source maps can be really large. So again, then I would like to see some improvements inside of the engines, how they handle source maps, because that's like an XY problem, right? You see a latency spike in reading the source map. So deploying TypeScript might be a better option. But what about the true source of the problem, that the engines doesn't handle source maps really well because they do it from JavaScript, and a source map is basically a huge base 64, especially base 64 encoded. It has a special format, I don't remember the name of it, where it has to have a copy of all your code basically again, and the reference to the translations, so you can find the original source code. It all has to be handled by the engine itself. So maybe if we can make that better, it won't be a problem, and you won't have the severe latency hit, and you won't have pay the penalty of doing translation at runtime.
Another idea that I've had for a long time is Lambda probably needs something like a Wasm runtime, because Wasm has got all of these bindings. So potentially you can have one runtime that can support different languages, because you can transpile Node, you can transpile C Sharp, and whatever languages. Do you think there's any sort of legs to that idea? Is that just like a pipe dream?
Yeah, it also, again, it's a bit complicated here, because with Wasm you basically have to ship a runtime within a runtime, right? So depending on what language you choose, you have to add all of the kind of standard library in there as well, which has been better. I'm no Wasm expert, so by any means, but my understanding is that one of the drawbacks is that the basic Wasm execution environment is very sparse, and you have to, if you ship C Sharp with I don't know if you even can do that, but say that you can ship C Sharp with Wasm, you have to you also ship the standard library, so you get all of this duplication of code. Whereas the C standard library is extremely lightweight, or the Rust standard library, you can remove the shared parts and have it present already as libc somewhere. Or with JavaScript, you have all of the standard library inside of Node and V8 and all of that, right? So you get a lot of duplicated code, which contributes to the size of the Wasm artifacts. And that is not also something that is very, very good for cold starts, because they have to come from somewhere. You have to load them. it has a kind of a tiered cache. So at the lowest level tier is kind of S3, where it has to be pulled, but usually it's a bit closer to the workers, but it still has to be loaded somewhere, which adds to this cold starts. So it's a bit of a mixed bag there if you get good performances, not, but it's a fantastic technology that allows you to pull in pretty much whatever you want. But then I would argue that then you can as well use custom runtimes and pick and choose. But you cannot, to your point, pick and choose inside of or it would be tricky at least to have a single Lambda function with multiple languages in the same function. It's possible today with custom runtimes, but that will be pretty bad for both cold start, and interfacing between them would have a significant hit on latency.
Okay, that will explain why no one's tried it yet.
There's probably people already done it, right? But I doubt that they will see the lower levels of latency as we see with basically every provided runtime. So I don't know, but I suspect it will be hard to get that below 200, 300 milliseconds. But someone can maybe show me something that they have done. But people are really innovative and smart. They probably find a way to do it efficiently as well.
We'll see.
Yeah.
Richard, thank you so much for taking the time to talk to us today, and great work on the LLRT. I'm really looking forward to what you guys are able to achieve this year with the runtime, and I definitely would suggest anyone who's listening to go and try it out and help the team with reports and finding bugs. And so we're all going to be able to get this really fast, super fast runtime for Node.js hopefully later this year.
Yeah, hopefully. We will work hard on it and try to make it, more compatible and support a richer API footprint. And again, Jan, thanks for having me here. It was fantastic talking with you. And thanks everyone for trying out LLRT and for all the, cool words and kind words that people have been saying. It's been so rewarding to see all the buzz. And again, I want to give credit to both Fabrice Ballard and Chase Gordon, who made a QuickJS engine, and the people behind our QuickJS, the binding layer, and all the Rust community that has also been tremendously helpful. So without that, this would not have been possible. So again, awesome that you guys want to try it out. Continue keep the bugs falling in, and we will take them off one by one, hopefully. So it was awesome talking to you.
Likewise. Thanks everyone for listening. See you next time. Okay.
Take care.